All right, we got 4 projectors today. That's fantastic. Okay, now you should hear me. How is everyone? How are you guys doing? Good? Managing? Too loud. Okay. Any questions, concerns? Fun plans for the weekend? Homework? Okay, cool. Let's zoom out a little bit here. Okay, so we are diving into proofs today. It is fun. Direct proofs. And it's going to be over integers. Okay. Why are we teaching you guys proofs? Cruel and unusual, yes. That's the primary reason. But there are others. We have other ulterior motives. So proofs are useful to validate design and justify use and or investment. Let me write this down for you guys. Proofs. Useful to validate. Let's just say a design. Okay. And justify. Use and or investment. Okay, well, that's a little bit different, right, from what you guys probably were thinking of proofs. So one of the really important results in distributed systems was the Paxos consensus mechanism. Okay, it's a terribly inefficient protocol. It's terribly described. In fact, I teach it in my distributed systems class, and there's like the first description of it where this guy who's brilliant, he presents it as like a voting scheme in like a fictional Greek island, and like no one understands what he means. So then he publishes another paper, which is like, I think it's something like Paxos Simplified, where he explains it mathematically, and people still don't like really understand it. And finally, people at Google implement it, and they're like publish reporting Paxos or implementing Paxos, and then everyone's like, oh, okay, right? So it was this terrible mechanism to begin with. And what was awesome about it, though, is that you could actually prove that it was correct. You could have a proof that multiple computers agreed on a particular value, right? Agreed who was the leader, agreed on a sequence of events, right? And before that, you couldn't really do that. You had like probabilistic guarantees, but you never knew when a bunch of systems would think that 2 of them are the leaders, the network would split in half. You would end up making some change where you do a bank transfer, but it actually doesn't happen when you read it from another computer, right? And so this algorithm, among some other advances, enabled Google to scale its infrastructure and make its search engine fast, right? This was one of the key advances. And they're able to do this because Paxos was provable, right? So, I mean, there's other kind of, famous proofs, but this one is kind of close to my heart, right? And so then when I look at, blockchain mechanisms, or I consider proposing my own blockchain mechanisms, I need to convince people not just like, oh, look, I implemented it, it works. No one's going to use it or invest into my startup if I can't prove that the mechanism is correct. Okay? When I can prove that something is correct, I can also stop worrying about it and just build on that thing as an axiom. And so it's a really important tool that you can spend a decade implementing something and you'd be like, look, it works like all of the time. Or you can spend like, 6 months coming up with the proof and achieve the same thing 100%, not probabilistically. Right? Which one would you rather do when you're trying to do a startup? Spend 10 years developing a prototype that you might not get money for, or spend a year writing a white paper that people are like, oh my God, let me give you, $10 million to try this out. Okay, so the other thing is proofs are useful to prove statements that can be used as axioms. Okay, so once you know that some little piece is true, you can use it as true. You don't have to reprove the whole thing over and over again. And you can start creating these building blocks that you can then string together to create proofs over higher levels of abstraction. So that's a way of getting to more and more complicated proofs. And so the ability to prove something or to say that something is true or that it's true under certain conditions requires you to have some domain knowledge or knowledge of mechanics in a domain, right? For example, you need to know how addition works or subtraction works. Right? There are these certain mechanics, and then there are methods of proof that you can apply to prove certain statements, right? So there's some mechanics and some methods that we need to learn, but as you get to like 400, 500 level courses, as you get to your jobs, this will be useful to you. Okay, so it's not just pure sadism that we teach you these guys. Questions? Okay. All right, so let's start with some definitions of things that we will use, right? And then we'll kind of look how definitions can be used as proofs, as building blocks. Okay, so how would you define odd and even? The concept of an odd or an even integer. Okay, so let's start with even. What does that mean to you guys? Divisible by 2. Okay. That's pretty good. There's a slight problem with this, that definition requires on a divisible operator, right? It's kind of, how would you write that formally, divisible? Okay, so we have some integer x, and then we modulate it by 2, and that should equal 0. Okay. This operator is a little bit tricky. It's actually a composite of multiple operators, right? So that can make proofs kind of complicated. But that's a good definition. If I was writing code, how to test it, that's what I would do. All right, so that's totally solid. The other way we can say this, so this would be even. The other way we could say this is that our some integer x equals twice some other integer y. Right? And so this is a slightly, it means the same thing, except we have this multiply thing, which is a much friendlier operator to us. So we'll go with that definition, and you'll see why. You'll appreciate it, hopefully, by the end of the lecture. Okay. So let's say that we'll write this formally, that for all x that are elements of the integers, okay, we're going to say that there exists a y that is also the element of the integers, such that even x, okay, the even over x is a preposition. Yes. Yep, thank you. Okay. So even x is a preposition. It's like the p of x or q of x. We can say even of x. Okay. Is true if and only if x equals 2y. Okay. So any integer x is even if there exists some integer y such that this whole statement is true. Right? Even if and only if x equals 2y. You guys good with that? Okay. So then we can get to odd, which is for all x element of z, there exists y element of z such that odd over x, if and only if x is equal to what? Yeah? Yeah. Or 2y plus 1. But yours works too. Okay. Great. So we got two definitions, and now we can decide things. Okay. So our question is even or odd. So 0. Even or odd? Why? Exactly. Okay, 2. So 0 actually equals 2 times 0. Okay, so x is 0, y is 0. Definition holds. We're good. Okay. Okay. Negative 301. Odd. Why? Okay, because negative 301 is equal to what? (151). Very good. Okay, so 2 times negative 151 plus 1. Okay, not negative 150 minus 1. You got to keep the plus 1 because that's our definition, if you define it that way. Okay. All right. Pretty good. What about this? 6a squared times b, where a and b are elements of integers. Even or odd? Even. Good. Okay, even because 6a squared b equals 2 times 3a squared b. Okay? So you can see that this definition is quite useful, right? You can look at anything and kind of see if you can find another integer that is that you can multiply by 2 to get to the original number. Okay? So there's a question here. How do we know that 3a squared b is an element of integers? Right? So our definition holds only over y being elements of z. So if you're going to use this as a justification, you need to now make sure that 3a squared b is in fact an integer. Okay. It's now the only operator that will result in that. square root of 5. Right? So, but you have your own to something, right? So it turns out that integers, the set of integers, is closed under addition, subtraction, and multiplication, not division, as you mentioned. What does it mean for a set to be closed? That means that if you take any two elements of the set and you apply one of those operators, you're going to end up with another element in the same set. Okay? Which is useful because now we can define integers or at least operators on integers that kind of stay in that set. All right, so this is kind of, we have some definitions, we have some mechanics around addition, multiplication, subtraction, right? And we're combining these pieces to make arguments. Okay, so any kind of system that you want to work in, any system that you're interested in, right? You may not be interested in integers. I'm not particularly interested in integers, right? They're just a nice system to work with that is semi-intuitive to us because we've seen it so many times, and it's, we kind of understand the mechanics of it. It's kind of predictable, right? So I'm not teaching you guys math. I'm teaching you methods here. There is some math that you'll need to know eventually in this course for computer science, but this is not it yet, right? This is simply mechanics over some system. Okay, so let's do another one of these. We need two more pieces here to make this interesting, okay? So we're going to define prime. Okay, prime over some integer x. Okay. This one's a little complicated, but it's not that bad. Okay, so for all x, elements of integers. Okay, and now we're going to go for all r and s elements of positive integers. Okay, so just like we have for all there exists, we can say for all, right? Because really for all z, then we're saying another statement is true, right? And so we can begin that another statement with another for all. We're good. Okay. We're going to say prime x, okay, if and only if parentheses x equals rs, okay, if x equals rs, then r equals 1 and s equals x, or r equals x and s equals 1. Close, close. Whew, made it. Okay. So what I'm saying here is that an integer x is prime if there are two other positive integers such that their product is equal to x, right? Those are factors of x. And the only way that you can choose such integers is if one of those is 1 and the other one is x, or vice versa. Right. And then we can define a composite number. Let's put it here, save some space. Composite of x. X is a composite number if for all x elements of z, there exists rs elements of z plus such that composite x if and only if x equals rs and one is less than r. One is less than r, which is less than x, and one is less than s, which is less than x. Okay. So what I'm saying here is that a number is an integer is composite if there exists two positive integers such that their product is equal to x, and then those positive integers are not 1 or greater than 1, so not 1 and not x, right? So somewhere between 1 and x, which means, like, for example, 6 would be a composite number with r equal 2 and s equal 3. We're good? Questions? Yes? Okay, let's see. So you have, okay, so we have 10. So we have prime 10. We're trying to see. Okay. Right, it's not a prime. Okay, let's see if I look this up. Okay, okay, so then if we have RS could be 1, RS could be, R could be 1, S could be 10. We're not worried about that case, right? We're worried about the other case, which is like 2 and 5. I guess that's the only other factor. Okay. So that equals 2 times 5. Okay. So let's say R equals S, 2 equals 5. Okay, so there's no 1 in here. Right? Good, that's good. I mean, it's a good question, right? Like, does the definition work for the case that's clearly not what we want? Right? So, okay, we can ask then a question like what about, okay, so we had a question about 10 now. Okay, not prime. Not prime. Okay. Say what? It is a composite. Yes, composite. Yes. Okay. What about 1? Ooh, wait. I think my definition's wrong here. So 1, okay, so 1 equals 1 times 1, which would mean that this is prime. 1 is not prime, you guys. All right, I tried to be clever and rewrite the stuff that was in the book. That's not good. Yeah, 1 is not prime. I can do better. Okay. So we're gonna do if. Okay. So we're gonna take this. Do I dare fix it on the fly? I guess I have to. In technically, yes, but we need to write this definition in a way that also does that. Right? So what we can add is, I'm just trying to think, okay, okay, so this condition or this condition, okay, and then after this, we're gonna say and are not equal to S. Okay, we're good. Is that going to go for both of them? You mean for composite? So it's going to be just for composites. I think it's okay, because if they're equal, if R and S are equal to each other, like let's say you have 4 is a composite, 2 times 2, I think we're okay here. Yeah. Yeah. Okay, so we have a third component. Okay, good, great catch, guys, great catch. The way the book defines is a little bit different. I tried to kind of make it so it looks like the definitions we've been doing, and clearly I dorked it up. Great catch, thank you so much. Okay, but we know what a prime is. We know 1 is not supposed to be a prime. So now with this, we know that 1 times 9 is not a prime. Yep. Yeah, not a prime. Okay, cool. But if you have questions about the definition of prime, the book does a good job. This is known. Don't get confused by my earlier mistake. Okay. So now we can ask a question such as, is every integer greater than 1? Okay. Either prime or composite. It would maybe seem like it. And so when we're trying to prove stuff, a good place to start is to ask yourself, like, does this seem true? And you don't know if it's true or false yet, but it's good to have some bend. If you think it's true, well, then try proving that it's true. If you think it's false, then try proving that it's false, or disproving that it's true, right? If you have no idea, well, pick one and just go after it, and then maybe you'll figure out something that you should actually have gone the other way, right? So we got to start somewhere. So let's say that it's true, right? We're not going to do a formal proof here, but just to give you guys kind of an idea, right, how to work with these definitions, we can say that X is equal to RS, okay? And then, depending on which way the chips fall, either R equals 1 and S equals X, or R equals X and S equals 1, okay? That's going to be true of any X, okay? So, any X has this potential, right? But now we can say there might be other R and S. Okay? So if those are the only R and S, then we know it's going to be a prime. Okay? To know that it's a composite, we really don't care about these. We just want to make sure that there are other R and S which are not 1 and not X. Okay? So if they are other, then we know they're going to be not that, because those are already grouped here. So then R and S would have to be between 1 and X. And then it would mean that it's a composite. So very informal proof, not a proof technique, but just kind of a way to see how you can maybe construct a proof based on 2 definitions and linking some logic between them. Okay. Questions? Moving on. Okay. So next, we're going to try to prove proving existential statements. Okay. So let's say that there exists an X element of some domain such that Q of X. Okay? What would make this statement true? How can you prove it? You find 1x. Find 1x and you say to me, it's 5. And Q of 5 is true. Okay? So you can give me an example. Okay? So you can do a proof by example. Okay. What if I had for all x element of D, Q of x? Could you prove it by example? You could not, because you would need to prove it for every single x, not just 5. Okay? You think it's silly, but like at least a quarter of you will try to do this in your homework. So don't be in that quarter. Look at the 3 people next to you. Or, yeah.
Could you prove it by saying not all of not two?
Not all of. You could form a contrapositive and then prove that. Okay, wait. What are you saying? Let me dive in. Okay.
So we had the such that and we had the all of.
Mm-hmm.
They're kind of opposite in disproving each other previously. So could we almost like do the opposite and use them to prove each other?
Yes, there is a path. Let me not go over this right now. This will confuse people. But if you have an idea and you want to explore it, let's talk. And for the rest of you guys, at the end of it, it should become clear kind of what you can do. Okay. Okay, the other thing you could do is you can do a constructive proof of existence. Proof of existence. Okay, so, all right, let's say, so the example is, the proof by examples, usually I'm not going to go there, but let's say that we have this type of thing. There exists a K, R, and S, all elements of integers, such that 22R plus 18S equals 2K. You could give me an example of K, R, and S that meets this definition. Okay? It's not immediately obvious what that might be, right? I mean, it's not that hard, but it would require some calculations. The other thing you can do is you can say we're going to let K equal 11R plus 9S. Okay? And then we know 2 things. K is an integer. How do I know this? Okay, so K was supposed to be an integer, and now we define it like that. R and S are integers, and we only have multiplication and addition, which means we have a closed set, which means the result is going also to be an integer. Good. Right? If you define K as like R over 2, right? We don't know. You don't know. You can't say. Okay? And then we know that, based on that 2K, okay, is equal to 22R plus 18S, which is what we were trying to prove. Right? So we just multiplied both sides by 2. Super simple proof. Okay, what does this tell me? Well, it tells me that an answer for that is R, S, and K defined as 11R plus 9S. I'm giving you a method of constructing an example, or you guys are coming up with a method of constructing an example rather than giving one. And so if your construction method satisfies the definition where we're saying k constructed like this is in fact an integer, we know r and s are integers, so that's fine, right? And then we're showing that, if you define k like that and you multiply it by 2, you get this value, which is what you were trying to get. And so your proof is closed. This is your example, or a method of construction. Okay? Yeah. Sure. So r and s are both integers. Okay? We know, and 11 and 9 are integers. Okay? And we know that integers is a set closed under multiplication, subtraction, and addition. So those are the only operators here. The result's going to be an integer. Right? And that's something that I'm asking you to believe in. There is a proof of that on which we're kind of building our proofs, but we're not worried about that. Okay. Okay, so, all right, let's do an exercise. Let's say there exists x, r, and s, okay, elements of integers such that we have an odd x, okay, and even r, and even s, and x equals r plus s plus 1. Okay, true or not true? True. Okay, someone give me an example. No? 5 equals 2 plus 2 plus 1. Great. That's our x, that's our r, that's our s, plus 1. Problem solved. Good job. Full points. Okay? But now there's part B to the problem. Okay? Prove by proof of existence.
We're only using addition, and then r and s are given as integers, so they're all in the closed set of integers.
But it's not clear that any set of integers would do this, right? If I give you x equals 5, r equals 3, s equals 2, it doesn't work, right? And it doesn't work because I said r is 3, but it's not even, so not a good example. Yeah. Absolutely, absolutely, yeah. We'll construct, yeah. You can, and that would be an example. That would be a proof by example. But if you're doing proof of existence, that's not enough. You need to kind of give a formula, right? So, okay, let's look at this, right? So we need to apply some variables, some definitions. Okay, so if we assume that we have an odd x, Okay. Kind of pull out some of that proof, right? We'll take the qualifiers out, but basically that would mean that x equals 2I plus 1, where I is an element of the integers. Okay, so because we know that x is odd, we know that there is such an I, such that I is an integer, and there it is. Okay, so we also know that there's an even R, okay, which will translate to R is equal to 2J, not necessarily I, it's a different integer, right? So there's no correlation, and we know that there's an even S. If and only if there's an S such that 2K. Okay, and then J and K are also elements of the integers. Okay, well that's handy. So now we can do this thing with let. So we're going to let x equal to I plus 1, R equal to J, and S equal to K. Okay. Such that I, J, K are part of integers. I'll be formal about this. I, J, K elements of integers. Okay? There's something really nice about this that's sneaky. Okay? We're saying that there's no restrictions on I, J, and K other than their integers. There could be any integer. Not odd, not even, any integer. Okay? We just bought ourselves a lot of freedom here in the definition. Okay, so we can then kind of substitute. Okay, so we have this part, which we need to substitute. So we have x equals R plus S plus 1, which by substitution we'll get 2I plus 1 equal, hey, remembered on my own, 2J plus 2K plus 1. Okay, so we can subtract 1 from both sides, and we get 2I equals 2J plus 2K. Okay, and now we know that I equals J plus K. Okay, and we know that I is an integer by closure. Okay? And there is your solution. Right? So you can take any integer I, any integer j, and any integer k, such that this is true, then translate those into x, r, and s, and there's your example. Right? So I can tell you that so for I equals 2, j, k equals 1, this works. This would basically be this example we came up with. But also I can tell you that I equals negative 371, j equals 251, and k equals negative 622. All right, so if we have this proof of existence, we can use it to come up with many, many, many examples much more easily. And there's kind of the power in that. So, I don't know, if you guys love it, that's great. If you guys don't love it and you feel this is fiddly and kind of slow, believe me that when you work on more complicated and excited things that you actually do care about other than integers, you end up using the same tools, right? Having these skills ends up making your life interesting down the road. So just kind of bear with this. If you're frustrated. If you're not, great. If you're not, you should go into computer science theory. You'll do a lot more of that. Okay. All right, let me do one more thing real quick. And that will be done with kind of preliminaries. So if we're going to disprove disproving, let's go with disproving universal statements. Okay. So if we wanted to disprove for all x element of D, okay, Px then Qx. Okay, we can disprove this by counterexample. Okay. Which would be to say there exists an x element of D such that P of x then not Q of x. Okay? So, to disprove a universal statement, you negate it to get there for all to there exists, negation of this, boom, boom, right? And then you can prove this, and if this is true, then the original statement is false, right? If the negation of the statement is true, then the original statement is false. Okay? And so we can do a quick example where we have to disprove, okay, for all a, b elements of the real numbers, we can have a squared equals b squared implies that a equals b. Okay? We don't like it. Feels wrong. Feels wrong. But to disprove it, we need to find a counterexample. Okay? Where there exists, an A and a B elements of the real numbers such that a squared equals b squared, but that implies that a does not equal b, or if then. Okay, and so we can find a counterexample where a equals 1 and b equals -1. Okay, so the squares are equal, but the numbers are not. Yes? Oh. Yes, I would. Yes, I would. Thank you so much. I would very much like this to be correct. Thank you. Okay, so the negation of P, then Q is P and not Q. Good. Okay, so let's stop here. We will get into the more interesting things. So these are kind of the easy things. Next, we'll get into proving universal statements, which is where the interesting stuff really begins. Thank you.
With the proving